Okay, good afternoon. My name is Matthew Conte. I'm a software engineer at Northrop Grumman Mission Systems in Baltimore, and I'm going to talk a little about a new approach that we took to developing test scripts on one of our programs that helped us save a lot of time in the INT phase, and that was successful for us. This is just the overview. So just a quick look at the kind of stuff we do. I'm in our space system software group. Generally, our flight code is written in C, C++, and runs on the VxWorks environment. More relevant to this presentation is our test software side, where we have a test environment written in the TCL or Tickle scripting language. I don't know if anyone is really familiar with it or how popular it is outside of Northrop. We have our environment we call test executive or test exec written in TCL, and all of our test scripts written in Tickle as well. And just to look at our group for the INT phase of this program, there were the usual breakup of software engineers, test software, flight software, and also systems engineers who are sort of like our subject matter experts who are designing the tests that we would have to develop. So this is an overview of our INT setup, which I think is probably fairly typical. We have our unit under test, which could be flight hardware, test hardware, or like you heard about yesterday, our virtual systems integration software. So on the unit under test, flight software is running. And then on the test side, we have our STI, or ground support equipment, which is controlled by the test software. And the general way of running test case is that the Tickle script would set up your STI for whatever configuration you need, send command sets over to the flight software, then after it was done running, pull telemetry data files back and run analysis to make sure that everything worked as expected. So getting into the problem you were trying to solve, this is our classic approach to developing test scripts. So the systems engineers would come to the test software team and kind of describe what they wanted their test case to do. It was almost kind of like a client relationship. We would have to do requirement solicitation, try to get out of them what exactly they needed all the test equipment to do, what kind of analysis they needed. We would then go and code up a Tickle script to do all this, give it to them, let them run it on the test bench, and then, of course, nothing ever works on the first try. So they would be sitting there on the bench. They would be getting bugs in the code or not getting the data that they needed. And then they would have to come back to us to fix that. So this system was inefficient for a couple of reasons. First, bench time is a pretty hot commodity. Like, we have limited hardware. Everybody wants to use it, so you're lucky to get like an hour or two a day. So if they're getting test scripts that don't work because we misunderstood their requirements or we didn't really know what they needed, it's wasting their time, and it's just delaying the integration and test of the system. But the root of the problem is that this cycle is basically asking people to do things outside of their area of expertise. So it's putting a burden on the test software engineers to understand like the specifics of every operating mode of every test that the system subject matter experts need to do. And it's also asking our systems engineers to debug these scripts. Most of them are not that familiar with software, or if they are, they know MATLAB for analysis, but not Tickle. Though to be fair, most software engineers don't know Tickle either before they come onto our team. But basically, the root of the problem is that you're asking people to do something that's outside of what they do best. So what we wanted to do was to fix that by letting everyone concentrate on their area of expertise. And so, as we'll see later, we came up with this test definition format, which is spreadsheet and parameter based. So the software developers, they built up this infrastructure, kind of like behind the scenes in our test executive environment, which is able to do everything that the systems engineers would need. So setting up your STI, requesting data to be pulled off the flight software after the tests, running analysis tools. And then we would provide an API to them in the form of a spreadsheet, which they can use to specify their tests. So the reason that this is more efficient is that you have software engineers writing code, which is what they do best, and the systems engineers can define tests on their own without trying to give requirements to us where there can be misunderstandings. and they can build the test themselves without having to look at any code. All they need to do is understand the spreadsheet and all the parameters available to them. And I'll show an example of one of these spreadsheets in a little while. So the spreadsheets are composed of what we called knobs, which are basically just parameters which can take in a parameter which can take in any values to set some kind of setting in your ST. And that terminology comes from the physical knobs on the front of a device, like a signal generator or an oscilloscope, where you would go in, turn the knob to get it to the setting that you want, except now we're doing it in software. But our knobs are also able to do some other things. So besides just setting up the equipment, they can also specify options for how to run the test. There was some talk yesterday about doing test like you fly and when it's appropriate and when it isn't. So we had a knob that said, if you set this to true, we'll run in test like you fly mode and be very strict, do everything like it is on orbit. And if you turn it off, we'll be more efficient so you can get more data out during testing. And they can also be used to queue up analysis tools to be run after the test to verify the output. And all these parameters are put in a spreadsheet, which serves as your test definition instead of a script. For the sake of safety and convenience, we defined default values for every knob and store these in a separate spreadsheet. So the reasons for this is that we had about 100 different knobs that you could specify, but most test cases only had to use 10 of them. So whoever was creating the test only has to put in the knobs that they care about. And for safety, so that at the end of the test, you can reset everything to a well-defined default state to keep all your equipment safe. So here is what one of these test definition spreadsheets looks like with an example of each of these kinds of knobs. So first one, like I mentioned, the options for test execution. So this knob is called the test like you fly. So if the default is off, but if you want to run in a strict test like you fly mode, you can set it to on. You can also set the frequency of our signal generator. So for this test case, it would be set to 1,000 megahertz. This is just an example. And also, you can use it to tell the software which tools to run at the end of the test. So we have this tool called analysis utility, which parses your log file and makes sure all your expected messages are there. So in this case, we're saying we don't want to run it. So what's interesting about this that each Excel workbook can be used to define a whole group of test cases, which in this case would be the 999 series of tests. And for this group, you have one column for defaults, which would probably be your most common settings for this group of tests. And then every other column is one specific test case in this group where you can override the defaults. Going back to the point of efficiency, if a test developer needs to add a new test case, all it takes is adding a new column in this spreadsheet. They already inherit the defaults, so they just reset the parameters there for whatever they need for that specific test case. So if they don't know Tickle or they're not code savvy, it doesn't matter because all they need to do is modify an Excel spreadsheet. Yes. So a little behind the scenes about how this works. In our test exec environment, we have what we call the translation table, which maps the names of the knobs that you see in these spreadsheets to certain callback functions, which would then go out to the devices over the lab network and actually set these settings as you requested them. They're split up so that they can, when they'll run. You can run them at the start of the test, at the end of the test, or during the test, whenever you need. And so yeah, that's just a mapping from the knob name to a callback function. This little animation will be kind of like the flow of how we parse this spreadsheet. So at your operator console, you select the test, click go, and the test exec environment parses your spreadsheet and reads out all of the knobs that you have defined. So first, they go through the translation table. We figure out what you're telling us to do. We have this code module called the Test Equipment Manager, which keeps track of all the ST equipment that you have, and then dispatches those calls over the lab network to the specific device. So these are just some example devices that we have, and which are available for you to control during your test. We also store these variables in a global array, which is not the nicest way of doing it, but for our first attempt, it's how we did it, that can pass the knobs to the entire system. So for instance, another code module called the analysis manager, he knows which analysis tools have been requested. So at the end of the test, it'll kick off these tools, which run on our another server, pull the data, like your log files and telemetry, and run any analysis on them. And so really, I guess the bottom line of this is that this now becomes your test script. So instead of going line by line and saying, set the signal generator to this frequency, set the oscilloscope to that frequency, a test script, all it really needs to do is say, do your pre-test sequence, run the scenario, which will trigger reading in from the spreadsheet, and then do your post-test sequence and cleanup. So for adding a new test case, you simply add a column to that spreadsheet, and you can literally just copy and paste this function. It's flexible enough so that in the rare cases where you need to do something custom in code, the test software people can add in specific function calls in here. But we saw for the vast majority of our tests, they follow this pretty simple format of set up the equipment, run the command set, and then reset the equipment to a safe default. One other artifact that we generated was a manual which explained exactly how to use all of these, because obviously if you have an API that's not documented, people are still going to come and bother you asking you how to use it. So for every knob that's available, we have all the parameters that are required for it, different ranges that they can accept, what each parameter means, and this is provided to our systems engineers and other test developers, so they can have it as a reference as they create their test cases. Just to sum up our results with this new methodology, we were able to get that efficiency that we wanted with everyone working within their area of expertise. Some numbers, only about 17% of the 1,500 test cases that we used were developed by the test software engineers. Everything else was able to be created directly by the systems engineers by creating the spreadsheets. So for all those test cases, you can imagine if we had to get requirements from them, there's a lot of room for misunderstanding. You have to go back and forth to debug your test scripts, and that was mostly eliminated. So only in the rare case where a custom solution was really needed did the test software people have to come in the loop on that. One thing that's not here, just a quick lesson learned that we found. We needed to think a little bit more about configuration management of these spreadsheets. The configuration management tool that we use is ClearCase, and the default merge manager comparison tool doesn't handle Excel files very well. So a lot of the times we ran into conflicts when merging or delivering branches, and we would lose changes. So we need to think a little bit more about that format, perhaps a CSV format, which is easier to compare, not as nice for people to look at, or trying to use a different tool which can handle merging of Excel files. But that's just one area where we could have cleaned this up a little bit and made it a little more efficient. So that's all that I had, so there's time for questions if anyone has any. Anybody around with the mic?
Actually, I was just going to suggest not on. Hello. We have a project at Ames you and I need to talk about that used Excel as a display interface, and all the data was actually pulled in as an XML file, and then when you click save within the application, it would save as an XML file on a remote system. So that may be a solution that would work for you in your environment.
You mean for the output of the test that would come into Excel?
So basically your test spreadsheet would just be an empty shell. When you open it up, it would pull down the data, display it, you would modify it, and then when you save, it would then shoot it back up to the server, and you're not storing Excel files, you're storing XML.
So you just do it on the fly then for each time.
Yeah.
More questions? No. Okay, thank you.